Okay, Chapter 3, Voltage. Chapter 3, Voltage. After completing this chapter, you're going to be able to identify the 6 most common voltage sources, describe 6 different methods of producing electricity, define cell and a battery, describe the difference between primary and secondary cells, describe how cells and batteries are rated, identify ways to connect cells or batteries to increase current or voltage output or both. Define voltage rise and voltage drop. And identify the 2 types of grounds associated with electrical circuits. This kind of makes me laugh. You know, the big buzzword now is alternative energy, right? Alternative energy. And really, worldwide, we consume electricity. That's the form that we've pretty much chosen. Electronics, electricity. You know, I don't think there's any places that are installing oil lamps. You know, new hotel in the Caribbean. We light our place with oil lamps. No, we use electricity. And there are 6 methods of producing electricity, period. So when I hear about alternative energy, I kind of sit up. I'm like, wow, have they come up with a 7th method? No. As long as I have been in this industry, there have been 6 methods. There are only 6 methods. If you come up with a 7th, now maybe you're onto something. Those 6 methods are friction, magnetism, chemicals, light, heat, and pressure, period. The first one we're going to talk about is friction. Probably the most familiar is the Van de Graaff generator. How many of you are here familiar with the Van de Graaff generator? Let me try that again. How many of you here are familiar with lightning storms? That's probably the best example of friction producing electricity. Guy by the name of Ben Franklin figured that out by flying a kite in an electrical storm. One of our brilliant forefathers. It's amazing he didn't get electrocuted in the process. So lightning is a form of friction, caused by atmospheric friction, if you will, and that produces lightning. Another example is electrostatic discharge. When you walk across a carpet or you move, if you're wearing clothes, just that movement, you could generate static electricity. Tens of thousands of volts could be generated by you simply wearing clothes. Okay, the alternative is not wearing clothes. You wouldn't generate static electricity by doing so, but of course the world would be a different place. The Van de Graaff generator, some of you have maybe seen in a museum before. I've got one in the back room. It's out of commission right now, but there's a big sphere on the top of it. And then what it is a belt. Pulls electrons off the bottom, brings it up to the top, so the sphere becomes charged. And what we could do with that is if you were insulated and you put yourself at that electrical potential, you've maybe seen the pictures where people's hair is standing straight out on end. That effect could be created with a Van de Graaff generator. Friction, not really the best method of producing electricity. You know, I'm not going to hire tens of thousands of people to walk around on carpets and then, you know, touch a conductor and power cities that way. It just doesn't make sense. On the other hand, if there was a method of somehow harnessing lightning, now that would be something. That would be something. I don't know. How many of you are from the Seattle area, Northwest, originally your whole life? I don't know if you've ever had the opportunity to travel like to the East Coast, the Midwest. Monster storms, the tropics, monster storms. Storms that even jet airliners can't get above. You know, 60,000-foot thunderstorms. Just amazing. I remember a few years ago I was flying commercially down to the Caribbean. And on the way back, this monster storm outside, and even the pilot was talking about it, and he's like, you know, in my 30 years of flying, I have never seen a storm this big. And you just looked out, and the whole thing was just glowing, constantly glowing. It wasn't like lightning flash. Lightning flash was just constantly sitting there, just like throbbing, glowing. It was like, ugh, pretty frightening. So if you could somehow harness that lightning, that would almost constitute a form of alternative energy. Magnetism is the most common method of producing electrical energy. This is how we produce electricity using something called a generator. That generator could be powered by steam. That steam could be generated from nuclear power, coal, water, wind, gas, diesel. It doesn't matter how you rotate the shaft. The goal is you got to rotate the shaft. It's actually very devastating, the news from Japan. I was watching the news this morning, and I guess they upgraded it to a level 7 accident now, which is on par with Chernobyl. Actually, the amount of radioactivity that puts out could exceed Chernobyl if they don't get it figured out. It's really too bad. I'm not necessarily, I don't know if you want to call me a proponent of nuclear. I mean, I worked on nuclear submarines for, 8.5 years of my life. And it's pretty cool. I mean, it's hot because it generates steam, but you know what I'm saying. It's pretty innovative technology. Because you know how often I commute. And I gotta go to the gas pumps about twice a week with my car. And my car burns premium. High compression engine. I got to burn premium in it. You're talking about $50 a pop just to fill up my car for me to commute. You know how many times I saw my nuclear submarine refueled? 0. Just kept going and going and going and going and going. So you get a lot of use out of nuclear power. Commercial nuclear power plant, basically what they do is they refuel the reactor, start it up, run it at full throttle for 18 months. 100% flat out for 18 months. Then they shut it down, refuel it. Most nuclear power plants have multiple reactors, so when they're refueling one, they got another one that's up and running. And then just back and forth. There's in some cases 3 reactors. So it was actually getting quite a bit of momentum in the green movement. A lot of the folks in the green movement were like, no nukes, and they realized that it's pretty clean energy. Yeah, you got to worry about the nuclear waste afterwards, but it's really a devastating, not only for the folks in Japan, but also really for, energy efficiency and non-dependency on fossil fuel burning. So hopefully they could get a handle on it. I mean, nuclear power, all forms of energy are inherently dangerous. My fuel tank splits open on my car on the drive home and I burst into flames. That'll kill me just as dead as radiation, you know what I'm saying? So it's a matter of mitigating those risks. But I want you to keep that in mind. This is why, again, alternative energy. I've been to Holland before. They got freaking windmills over. Windmills. They were harnessing wind energy. Now wind turbines, All you're doing is rotating the shaft and you're turning a generator as opposed to grinding your grain with power from the wind. So is it really alternative energy? Nah, there's just a different spin on it. Which is interesting, because I've known this stuff since, puberty. And I always, in the back of my mind, was thinking about, energy in different forms. Because I was always getting yelled at by my parents, shut the door, shut off the lights. What do you think, you live in a barn? This type of stuff. So I was, at a very young age, I was thinking, wow, one of my duties as a child was cutting the grass. And it used to amaze me the small amount of gas I could put. I was always hoping I'd run out of gas, so I couldn't finish the lawn. Why? I ran out of gas. The thing would never run out of gas. It was this little tiny tank, and that motor would just keep, the engine would keep going and going and going and going and going. If there's a way of harnessing that motor to a generator, and that could, I could leave the lights on, I could leave the doors open, I could get my parents off my back. At a young age, I was thinking about alternative energy. And obviously, I didn't understand all the formulas associated with it. So, no, you can't necessarily power a home with a small 3.5 horsepower Briggs & Stratton engine. But with a 10 horsepower, you could do it. And if you've got a backup generator, that's a good enough size generator to power a home. Anyway, that's how we harness magnetism. The generator could be configured to produce either direct current. Direct current is the flow of electrons in only one direction, negative to positive, period. Negative to positive. Or alternating current. Alternating current is actually current that goes back and forth, back and forth. What comes out of the outlets here in the school and at your home is alternating current. The electrons never really go anywhere, but they're getting shaken back and forth, back and forth, back and forth. That's the harness, that's the energy that we harness. So we could have a generator connected to a shaft that produces either DC or AC. DC generators are not that prevalent. They're not that prevalent. Really, AC is used predominantly throughout the industry because of it's a higher level of efficiency in transmitting the power. This is the schematic symbol for an AC generator. So if you saw this on a schematic, you would say, ah, this means an AC power source, AC generator. Chemical. Chemical. The most common is a cell. Chemical means is the second most popular method of producing electrical energy. A chemical cell. What we're talking about here is batteries. The original chemical cell consisted of two metals, copper and zinc. These were the old school batteries. Remember the kind that if you left them in your device too long, they'd start to like ooze and ruin your portable electronic device? Those were just standard carbon or zinc cells, copper zinc cells. Typically, many cells can be connected to form a battery. When we use the term battery, we're actually talking about something that's made of multiple cells. And part of why I'm telling you this is that you're all here to learn a second language, and that second language is electronics. So if you were going to go to Fred Meyer, where are you going? I'm going to Fred Meyer to get me some batteries. If you said that to me, I'm going to assume that you're going to get batteries, and batteries are multiple cells that are put together. Where are you going? I'm going to Fred Meyer to get me some batteries. What do you need batteries for? For this here flashlight. That battery doesn't, that flashlight doesn't take batteries. That flashlight takes cells. And cells are the typical size batteries that we've come to know and love. AAA, AA, C, and my personal favorite, the D-size cell. D-size means it's bigger. Since it's bigger, it means it's got more chemical in it. More chemical means it's gonna last longer. If you had a D-size battery and you connected it to your remote control, it'd look stupid, but it would last forever. Okay? I put AAA batteries in my remote and they last for longer than my TV lasts. You know? I just had some cells go out in a remote. And I looked, they were the original cells of the remote. I'm like, man, I've had this thing for freaking 14 years. It's got the original goofy brand batteries that came with it, you know? So typically, many cells can be connected to create what's known as a battery. Now, in schematic diagrams, when you see this symbol right here, you can assume that this is a cell. The short line is the negative lead. The long line is the positive lead. On a schematic diagram, if you put a short one, a long one, a short one, and a long one together, we could make the assumption that this is a battery. The other assumption that you could make on a schematic diagram is when you see this, assume 1.5 volts. Because most cells, AAA, AA, C, and D, all produce 1.5 volts DC. So if we saw this, what can we assume? 1.5 plus 1.5 is 3. So normally on a schematic diagram, sometimes they'll draw 2 of these side by side, sometimes they'll draw 3, but they won't draw any more than 3. So anytime you see 2 or more, assume that it's either the value here, or right next to this I could write 12V. And if I write 12V, well, it's a 12-volt battery pack. And if you split that battery pack open, you would find that it's actually made up of multiple cells that are wired together internal to that battery pack. Make sense? Light. Light. Photovoltaic cell harnesses light. A single cell can produce a very small voltage. So therefore, many cells must be linked together to produce a usable voltage and current. These are primarily used in satellites, because satellites would look stupid if they had like an extension cord connected to them. You know, you'd be like, what the heck is that going up into the sky, you know? Well, it's an extension cord for, you know, communication satellite. So we can't do that. Cost is high, but it's declining. What I suspect is going to happen with this, photovoltaic, basically to make a solar panel, it uses the same technology that is used to make microchips. So it's a pretty costly process. What I suspect to see, and you're not going to find this in any textbook, what I suspect you're going to see is a marriage between photovoltaic and nanotechnology. And when those two merge together, you're going to be able to go to Sherwin-Williams and get paint for your house, and they're going to say, sir, would you like the photovoltaic additive today for $19.95? Sure, go ahead. And they'll add a photovoltaic additive, and the fact that your paint on your house is outside and it's in daylight part of the time, it's going to be producing voltage. Now, we're not quite there yet, but I suspect that that's where we're going to be. They do have the technology now that there are companies that basically could spit out photovoltaic film almost like Reynolds wrap. So you could, you know, go out and buy a roll of photovoltaic and roll it out and connect your connections, and you're producing electricity. So the cost is coming down on this stuff. And think about it, free voltage from the sun. I mean, how cool is that? I mean, it really is. Here in Western Washington, well, you know, you probably have to pressure wash it twice a year to keep the moss from growing on your panels. I got moss growing on my car. I'm getting in the other day, and I'm like, what the heck is it? Moss growing on it. But other areas of the country, they're doing this. They're doing this. I was in Arizona, Flagstaff, several years ago. And I checked into the hotel late at night and got up in the morning and opened my curtain of the hotel room. I was on an upper floor, and I was shocked. Number one, it had snowed out the night before, and there was like 6 inches of snow out there. I'm like, holy crap, this is Arizona. What's their snow doing out there? It's Flagstaff. You know, you're in the mountains. The other thing that shocked me is, wow, look at this. Across the street was a solar farm, and it was all photovoltaic panels connected directly to the power grid. And these panels would all track the sun and you know, basically supplying energy to the power grid. So in some areas of the country, they're already doing this. Would I rent out tonight and buy solar panels for your home? Probably not. But again, it's free energy, free voltage. So keep your eye on this technology, because I'd love to be an investor in the company that gets that photovoltaic nanotechnology harnessed. You know, just add a little pinch of it to your paint or whatever, and paint whatever, you just turned it into a solar panel. Science fiction? No. Guarantee you within the next few years we're going to be seeing that technology. This is what those solar panels look like. And the problem is this is on a metal backing, but basically it's glass. It's glass, so it's pretty fragile. You know, you want to have it permanently mounted. Still, for out of space, satellite, it's the best option. Point it towards the sun. The sun comes out every day. Actually, if you're in outer space, it never goes out. because you're not rotating if you're a stationary satellite just looking at it. Unlimited electrical resources. It was actually interesting. I was at a conference. I spoke at a conference a month ago. That was like a month ago today in Milwaukee, Wisconsin. It was at the Green Energy Summit. I was an invited guest speaker. And one of the other speakers was it was very interesting. He had one of our first satellites, a mock-up of it. And when they were developing the satellite, this was in response to the Russians launching Sputnik. And it was the whole thing with the space race. And basically, he who gets the satellite in space first and goes to space first is going to dominate the Earth, So this is all stuff that was going down in the 1950s. They, in a push to get our satellite up there in response to the Russian satellite, basically what they had was a battery-operated satellite. Launch it, goes up, beep, 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 beep. And that's literally all this thing did. It was a beacon, just beeping in space. And then as an afterthought, though, the engineers were like, let's put this on it. This here is a photovoltaic cell. Let's put this on it so that when the battery dies, it'll continue to beep. And they're like, what are you doing? This is stupid. This is stupid. This is not viable technology. Solar panel, photovoltaic cell. This doesn't make any sense. Well, they finally convinced them to put it on. Well, guess what happened after the battery died? Photovoltaic kicked on. And then it kept going and going and going and going. And I think finally it was like interfering with some other communication technology that developed. They finally had to shut the thing off. So that was proof of concept that photovoltaics really work. And of course, it's become mainstream ever since. This is a cool way. No, it's a hot way actually of producing voltage. We could use heat to produce voltage with what's called a thermocouple. These are two dissimilar wires twisted together. When I say dissimilar, I don't mean one blue wire and one red wire. I'm talking about two dissimilar metals. And they're not actually twisted together, they're actually welded together. So you get the two dissimilar metals, and then you weld them together. Where they're welded together, when you heat that joint, because they're dissimilar metals, it's going to produce a voltage. Voltage produced is directly proportional to the amount of heat applied. These are going to be used in thermometers. If you've seen a digital thermometer, typically that's going to be a thermocouple. Because what it does is you apply heat to it, it produces a voltage. The voltage gets converted to an equivalency of either Fahrenheit or centigrade. And then you read it out. Real simple way of doing it. Also called a pyrometer. Pyrometer. Had a student in this class several years ago whose father owned a company locally. I forgot the name of the company, but they basically produced thermocouple sensors. And one of the big products that they were developing was specifically for the racing industry. And what it was is about the size of my laser pointer. It was nice stainless steel, and it had a little probe on the end, and that was the thermocouple. And what was so popular in the race industry, I don't know how many of you are into racing or whatever, you take like NASCAR, for example, and ideally what you want to do with one of those race cars is set it up so that you distribute the weight evenly on every tire equally across the tire. And if you could do that, obviously you've got the most contact with the road. It's going to give you the most handling on the track. It's going to give you the best performance. Generally speaking, there are some exceptions to that on a road course versus whatever. But basically you want full contact with all your tires on the track. Make sense? Also understanding with NASCAR, rear wheel drive, right? You're going to have a lot more friction on your rear wheels. So what happens is when that race car pulls in and they pull the tires off, then they could sit there after they get the car out of the pits with their thermocouple probe and then measure across the tire, outside, inside, or outside, middle, inside, for my left rear. My right rear, take the same readings. My front tire, take the same readings. My other front tire, same readings. So you should see consistency between the two fronts across temperature-wise too. That means you got the car set up so that the tires are in full contact with the road. So it's really a poor man's alignment tool. So he gave me one of these. It's kind of cool because it's the OEM. It's just stainless. It doesn't have any decal or sticker on it. I mean, they're the factory that built it and then sold it to some racing company so they can put their name on it, and or snap on and charge an arm and a leg for the thing. So he gave me one of these things. So I actually did some experimentation. Since I am a commuter, I did that a couple times on my drive home. I was wondering what the alignment on my car was. So sure enough, I drive home, I pull off the exit hot, Federal Way, pull over the side of the road, get out my fluke meter with this thing plugged in, take temperature readings, look for consistency. I've basically been tweaking alignment in my vehicles using nothing more than that temperature gauge. Pretty cool. Pretty cool. Thermocouple. Simply applying heat to the device produces voltage. That simple. Apply heat, it'll produce voltage. This is what the schematic symbol for one looks like. Again, understanding that these are going to be dissimilar metals, two dissimilar metals, and then you weld this together, the bead.
So are they not actually twisted together like it shows in the picture?
Actually, because they're in contact with each other, it will produce.
Where would you take the reading at the very end of it?
On the tips.
Okay.
Yeah. So simply by putting the wires together, they are going to be in contact with each other, so you are going to get some reaction, but these thermocouple probes are actually welded. The tips are welded. Believe it or not, another method of producing voltage is simply by the use of pressure. This is called the piezoelectric effect. Piezoelectric effect. Voltage is going to be very small, so it must be amplified in order for it to be useful. But just a pressure change on a crystal will produce a voltage. This is used for crystal microphones, phonograph pickups, right? And precision oscillators, as well as some sensors, pressure sensors. You could get some really inexpensive pressure sensors now that are calibrated for barometric pressure, standard barometric pressure. So as the Earth's pressure, the atmospheric pressure changes on it, the voltage will change. You couple that with a weather station, or couple that with, actually you could use it for altimeter. If you're sending a rocket up and you want to know how high your rocket goes, you know what your base pressure is. As you go up in altitude, the pressure decreases. So you can have an inexpensive little sensor that keeps track of your pressure. Also, these are used in a lot of engine sensors now, right? You could monitor all types of different pressures, your oil pressure, your cooling system on board an aircraft, your hydraulic pressures, all of them. Little sensor. That voltage gets amplified, sent into a computer, and then you can look at all this virtual instrumentation. Simply doing it by applying pressure to a crystal. This is what the schematic symbol looks like for piezoelectric crystal. Now, we're going to talk about some different types of batteries. Battery, of course, is a combination of two or more cells. Now, we have two different choices of cells. One is called a primary cell, the other is called a secondary cell. Let's first talk about primary cells. Primary cells are cells that cannot be recharged. One-time use. These are like most of the cells that you and I buy, right? When you're done using them, you recycle them. Don't throw them in the landfill, right? You recycle them. Bring them to the hazmat place, and then they'll turn it in and get money and make your community more profitable based on you turning in your dead batteries. Some of the stuff you don't want going to the landfill. Although they've gotten better with the choice of chemicals that they're using. But primary cells, once you use them, you throw them away. This is designed after what's known as the Leclanche cell or dry cell, also referred to as the carbon-zinc battery. Carbon-zinc battery. This is the old school battery that we were talking about earlier. I got a couple old timers in here. Remember, that's all we had. These are the only types of batteries that used to exist. And then I believe it was in the 1970s they came out with alkaline cells. That's when alkaline became somewhat mainstream. Started to become mainstream. These alkaline cells were still pretty expensive as compared to the carbon zinc batteries. I remember Radio Shack, because again, I was a big electronics guy, so I was like hanging out at Radio Shack, like looking at all the parts and stuff. And Radio Shack used to have a Battery of the Month Club. And you got a little card, and you'd go in with the card, and you'd pick out the battery that you wanted, and then they'd punch your card, and you got a free battery. It was a carbon zinc battery, but it got you in the store. It's kind of a cool thing. Alkaline cells, really, really good. Alkaline cells would work a lot better with a lot of electronic equipment when it came into being. The latest cell, and my personal favorite, is the lithium cell. These are the high-end lithium batteries that Energizer produces. They cost like $16 for 8 batteries. They're very, very pricey. But these lithium batteries will produce a voltage longer than any of these other types of primary cells. They also have a longer shelf life. I'll bring in a package, we can look at it. I bought some last week, and I think it's the expiration date on them is like 2022. Some crazy time in the future. We won't even need batteries like that. We'll be flying to work in jetpacks and stuff. We won't even need lithium batteries. And the other thing that these are real great at is working at a variety of different temperatures, from extreme cold, which really kills batteries big time, slows down that chemical reaction, to extreme heat. They've kind of known about lithium batteries for a while, lithium cells for a while. On my airplane, there's something that's called an ELT, Emergency Locate Transmitter. In the event of crashing, there's a G switch that triggers a transmitter to start transmitting out a beacon that gives your position away. So search aircraft. Actually, they used to have satellites that looked for that signal, but now long story, they've switched those satellites off. They've gone to some different frequencies now, but it would transmit. So when this thing worked, it had to work. It's a safety device. Even like on a ship that goes down, they have these EPIRB systems that transmit to the satellite. You want that thing, when it has to work, you need the thing to work. So this has always been the choice for those types of applications, the lithium cell. I was really, really jazzed and excited when I saw these come on the market for a consumer-based product, because the lithium batteries before were unique, you know. To the manufacturer would put it together, and you'd have to buy the replacement from them. Because like the FAA requires every 24 months, you've got to replace that cell whether you've used it or not. So for them to come out, the sizes that I'm aware of, they have AAA and they have AA size. Have any of you here used any of those? Have you used them? Highly recommend it. If you're going on your dream vacation, if you're doing photography and you want something for your flash and you want that flash to keep going off and you don't have to worry about it. If you have if you're going hiking, I use it in my GPS. I have a backup GPS, that I use whenever I'm going off the grid or anything. I've got a pack. That I bought. Energizer will sell you a pack that you could use to recharge your cell phone. Have you seen those things? It's like a little pack, and it comes with those lithium batteries, and it's got a little cord. So like if you're off the grid and you got to recharge your battery, it comes with that style, your micro USB or mini USB plug or your Nokia. Everything now is micro USB. That's kind of the standard for newer cell phones. But you put those lithium batteries in it, you plug it in, and it'll give you another charge. So if any of you do any backcountry stuff or anything like that, I highly recommend you look into them. It's a wise investment, a very wise investment. It's the best primary cell that money will buy. This is you got the diagrams in your book, kind of a cutaway view of a standard carbon zinc cell. Another cutaway view there. Cutaway view of a 9-volt battery. Is this really a 9-volt battery? Is it really a battery? Yes, it is. It's made up of multiple cells that have been put together. Each cell is capable of 1.5 volt. So they put multiple cells together to give them 9 volts. Why 9 volts? Actually, this 9-volt battery is also synonymous with what was called a transistor battery back in the day. There's no transistors in it. Why was it called a transistor battery? Because this is the type of battery that your transistor radio would take. Growing up in Connecticut, I used to have a little small 8-transistor radio. Used to go to the beach, and I used to tune in my little radio, play music, listen to New York radio stations, playing all the top 40 hits and everything. 8-transistor radio. Took a 9-volt battery or transistor battery. This was typically the battery that I would get as a free battery at the Battery of the Month Club from Radio Shack. Why? My assumption was it's got 9 volts. The other ones have 1.5 volts, so I'm getting more for my punch, my free battery, than a 1.5 volt battery. So this was typically the bad boy that I always used to get for the purpose of experimenting. Secondary cells are cells that cannot be recharged. You're all familiar with this type of cell, the lead acid battery or wet cell, which is in your car right now. These batteries are not just used for automotive applications. These wet cells, these lead acid cells, are also used for backup power supplies by the phone company. For your landline, they're also used at cellular sites for backup power. In the event that power is interrupted to the cell sites, automatically they'll switch over to battery backup. They're typically lead acid cells.
That's what they use for like solar systems too, right?
Absolutely. And they use those for solar systems now because they're the cheapest secondary cell that's really on the market. There's other technology that's more efficient, that's more better, okay, but it costs more. So if you just want to, let's say you live out in the desert and you want to run lights by day and harness the energy by day, and you need a lot of solar panels and you're going to need a lot of secondary cells. The cheapest secondary cells that you could buy are lead acid cells. My submarine had a whole bank of lead acid cells located in the center of the submarine down in the keel, the very lowest portion of the boat. And it was called, ironically, the battery well. And in the battery well were batteries that were basically 6 feet tall, and they were about this big around, and they were individual cells. And it took a crane to be able to lower these things in and move them all in. And then they had wooden shims. Wax impregnated maple shims were all put in between these, and it was all one giant bank, and they were all wired up. Lead acid. On a daily basis, an electrician would strip all the metal off of their uniform if they had a belt on or anything metal. And typically what they had is a special jumpsuit that they put on that had all acid burns in it. And what they would do is they'd have to climb down in the battery well, and they'd have to check the gravity, the specific gravity. This is the electrolyte fluid inside. And basically, when we charge a battery, what are we putting into a battery? Who said electrons? Electrons. That's really what we're doing when we charge a battery. We're putting free electrons, we're storing it in an electrolyte solution. Are electrons matter? Absolutely. They're not very dense, but they still are matter. When you charge a battery, what you do is you increase the specific gravity of that fluid, that electrolyte fluid. So what the electricians would do on a daily basis is they had a clipboard and they had a grid that showed all the locations of the battery. They would go down in and they would check the specific gravity. You know what I'm talking about with specific gravity? Specific gravity is a comparison of the density of pure water, H2O at room temperature, standard temperature. The specific gravity of H2O, pure water, at room temperature, standard temperature, is 1. 1.000000. It's 1. It's what we compare everything else to. Now, if I have pure water and I start to get some salt and I dissolve salt into the water, what am I going to do to the specific gravity? I'm going to raise it. I'm going to increase the density of the fluid, and by taking a specific gravity reading, I'm going to show that it's more dense. That shows me that I've done what? I've put matter into the solution. If I dissolve sugar into it, same thing. If I pump electrons into it, what am I going to do? Same thing. I'm going to increase the density of it. I use specific gravity. I brew my own beer. And I use specific gravity to tell me what the alcohol content is. In the brewing process, I basically impart a lot of sugars into the beer. And I take that reading. The more sugars I put into the beer, the specific gravity increases. The density increases. Make sense? Then what I do is I get yeast. I put the yeast into that solution, and the yeast consumes the sugar, converting it into CO2 and alcohol. So after the yeast has done its job, I expect to see that specific gravity decrease because alcohol is less dense than water. And then I take my first reading, compare it to my last reading. That gives me my alcohol content of what's inside the beer. For a battery, your battery in your car has 6 cells. If you buy a hydrometer and you test those cells, you should get consistency across all of those cells. If you don't, if this cell's good, this cell's good, this cell's a little bit lower, this good, 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 this cell being a little bit lower, you're probably developing an internal short in that cell. You need to replace your battery. You can't just replace the individual cells. You have to replace the whole entire battery. So back on the submarine, they were really concerned about that on a daily basis. They sent somebody down in the battery well to take those readings, because if they saw a cell that started to develop an internal short or a problem, conceivably it could take all of that energy and dissipate that energy through that one bad cell. That's bad news. Because, oh, by the way, you know why we had a battery bank? If our nuclear reactor shut down or we had a problem, we could get to the surface. When we get to the surface, we could start up a diesel generator. So from that transit from the deep up to the surface, we needed to be on battery power. If you can't get the diesel started while you're on the surface, or actually at periscope depth, because we had a snorkel they could just stick up where it's you're in induction systems for the diesel engine. Run the diesel, we had a generator connected where we could keep not as much power as we'd have to nuclear power, but to keep all vital systems up and operational. Actually, I had a real scare once. We were someplace we weren't supposed to be, like someplace we were not supposed to be, typically where we always went with my submarine. And it was a national holiday for this country. So all of their, they'd take their submarines and drive them through Red Square and their tanks and their missile launchers and everything. And, we had nothing better to do. So instead of like, hey, we're watching the Soviets, they're having a holiday, let's us have a holiday. Because on the 4th of July, we're going to be watching the Soviets and they're not going to take into account our holiday. The captain didn't think it was a very good idea that I had. Now, as a matter of fact, Mr. Grenick, I think what we're going to do is we're going to do some drilling today. And it's firefighting or whatever. Well, we did a drill, an exercise that involved scramming the reactor. Sounds ominous, doesn't it? Scram the reactor. Oh no, don't scram the reactor. Scramming the reactor is actually a good thing. Scramming the reactor is when you shut the reactor down. You have control rods, you move the control rods in, you neutralize the reaction, the nuclear reaction. This is actually what they did too in Japan. After the earthquake, as soon as there was seismic activity, pow, they shut those reactors down, scrammed the reactors. The problem that they had afterwards was with the tsunami damaging, I suspect it was their intake, their seawater intake for used for coolant, and they couldn't dissipate all that heat that had already been generated, and then it became an avalanche, so to speak, of circumstances. Anyway, we're somewhere we're not supposed to be, and it was quiet. So the captain figures we're going to do some nuclear drill, scram the reactor, pow, scram the reactor. Normal procedure is we start to come up to periscope depth, make sure that we're not going to hit anybody up on the surface, come up, raise the snorkel mast, start the diesel generator. Well, they try starting the diesel generator, which was commonplace, wouldn't start. And what had happened is there was this multi-pin connector that for whatever reason disintegrated in the back of the diesel control panel. So it's kind of like, well, that's going to take 2 days to put back together, you know? So we're on battery power. To be honest with you, we knew it was a drill and we were all real sloppy, rigging for reduced electrical. That's where we shut down all non-vital systems. And we knew it was a drill, so we were very slow in doing it. We expended over half of our battery energy in that period of time. So now all of a sudden, the reactor shut down. We can't start the diesel generator, and we've just consumed 50% of our battery power because we were screwing around, kind of dragging our feet with this exercise. So we realized what was happening, and basically the decision was made, restart the reactor. Well, they try restarting the reactor, and the reactor won't start. And we've consumed all of our battery power. So now we went to this like super rig for reduced electrical, where there's like, you know, emergency lighting and all the environmental systems are down. So the air all of a sudden is almost unbreathable, and it's in excess of 120 degrees, and it's humid, and it's just miserable. Can't get the reactor started. And in my job, surveillance, I was down to one receiver. I shut all my sophisticated stuff down, and I'm down to one receiver. You can't make the story up. It's like, holy crap, here comes the fleet. It's like, what are you talking about? Here comes the freaking Soviet fleet, and they're headed right towards us. I'm like, you gotta be kidding. So it got really hairy, because this is the type of thing that like World War III could start over. What's a submarine doing in our harbor? You know, violating our sovereign territory and all of this stuff. You know, we couldn't get caught. So. Truth be told, they were able to get the reactor started. They had to kind of amend their procedures, and come to find out it was actually a reactor control switch had failed. It was a series of circumstances. We called that day, anybody that served on the boat in that era, affectionately known as Black Tuesday, because things were really bad. And I had it good. I mean, my space normally where I worked, I had to wear like a foul weather jacket to stay warm because of all the air conditioning. Of course, all the air conditioning was down, but I tell you what, the guys in the engineering spaces, I mean, they were stripped down to their underwear and no shirts, and they're just sweat pouring. I mean, it's temperature skyrocketed, you know, 150, 160 degrees back there in the engineering spaces, and you're trying to troubleshoot something. But anyway, it all worked out good in the end. But that's the necessity of backup battery. Now, a lot of you may be saying, well, I'm never going to go to work on a nuclear submarine or a ship or whatever. No, you might go to work as a biomedical electronics tech at a hospital. Guess what hospitals have? Backup battery banks. You might go to work for the Federal Aviation Administration. Federal Aviation Administration down in Auburn, Washington, at the Mountain Region Air Route Traffic Control Center. I don't know if any of you are aware of that facility. If you go to the Muckleshoot Casino down there, it's like right across the street. It's a big building, fences around it, armed guards, all kinds of stuff like that. That's where they control all the air traffic in the northwestern United States. From western Montana to the Pacific Ocean, from the Canadian border all the way to northern California. If you're in an airplane in flight, you're talking to somebody in Auburn, Washington. They lose the power at that facility, guess what? The whole northwestern United States aircraft are flying blind. So they were kind of smart about this. They put in a battery backup system. So as soon as the power AC crashes, these batteries have power inverters, and that brings it back up online so they don't miss a beat. Once the batteries are up online, then they have diesel generators in another building on the property that will go ahead and kick in, and they have huge fuel tanks so that they can power that for a very long period of time. If any of you have ever heard in the news in the past, a lot of times if they have a glitch like an air traffic control system and switching over to backup power, that's actually what the problem is going from AC to that battery backup. If it doesn't happen seamlessly, all of those systems go down. You all know with computers, you got to reboot computers, so you have aircraft flying blind without air traffic control for a period of time. So it could be somewhat of a inconvenience, safety concern. So a lot of you are going to see this. Actually, one of the most reliable systems, and this is I don't know how many of you still just have an old-fashioned telephone line to your home. POTS is called. And basically what that is an old school, just 2 wires coming to your house. Most of us now are on broadband and voice over IP and all this kind of crap. The old school telephones were the most reliable. You could have a power outage, you could have earthquake, whatever, and you pick that phone up and you're still going to get a dial tone, because that dial tone is being generated by backup battery banks at the central office, and that's powering the phone system. So, you know, I've experienced a lot of blackouts in my life where the power would go out, and I never lost that dial tone on the phone. Now, you know, how many of you are like with Comcast? You know, I mean, what was I thinking when I went to actually, believe it or not, I'm not just talking the talk, I'm walking the walk. Before I came to work today, I actually called Quest. I want to get an old school line back into my house, because I'm looking at my phone bill. My freaking phone bill, I don't know, I'm paying like $70 a month for, you know, caller ID and call waiting, and the only people that call me are people that I don't want calling me, okay? So why am I paying $70 a month to have something that I don't want? And I don't want to shut the line off because I have some other uses for that line. So I called Quest, and I'm like, it's kind of an unusual request. Do you have any of the old school lines that, you know, I could still have, you know? Yeah. And how much? $13.50 a month plus tax. I'm like, that's what I want. Can you port my existing number back to it? Yeah, no problem. So I'm going to get that scheduled. $13.50 a month. Now, you can no long distance or anything, but I don't want it for that. I want it for that 911. I want it. I don't know why I'm going to disconnect the ringer, because again, the only people that want to call me, they call my cell number, you know. But I still need that. If you have an alarm system at your home, you need it. If you've got a satellite TV box for updates and pay-per-view, you need it. So it could call into the mothership on a daily basis. So battery backups are still out there. So don't think you're not going to go to work in the industry and never see a battery backup. Now, you're all familiar with lead acid, nickel cadmium, NiCad. How many of you are familiar with NiCad batteries? NiCad have been out for a long period of time. NiCad's had a nasty habit of generating what was called a memory. And what that memory was, in essence, is if any of you have ever had your arm or leg in a cast and you don't use it, basically the muscles forget how to fully exercise your range of motion. You got to go through some therapy to get your arm working again, right? It's kind of the same thing with a NiCad. A NiCad, if you didn't fully discharge it and then fully charge it, it would only think that its range was in this narrow margin of performance. So the problem with NiCads with like camcorders and cell phones, where as soon as that voltage started to drop a little bit, you start to get the low battery indicator. And to preserve the electronic integrity of what you were doing, it would shut off. Then you'd get it, stick it in your charger, charge it back up, and what would happen? It would only get used to operating in this little realm right here. Some of the manufacturers got smart and they put a little button on there and they could connect it to a load and drag it down all the way and then recharge it all the way. Because I understand this stuff, I've gotten exceptional use out of NiCad batteries. When my kids were growing up, my first video camera back in the 1980s, I had one of those big VHS units. Don't laugh. It was VHS. At least it wasn't beta. Should have been beta. Beta was better, but that's another story for another day. But it was one of these big Herkin VHS, you know. And it took this big 12-volt battery pack. And I went to replace it. And I was looking at some different vendors, and they were looking at me, and they couldn't believe that it was the original battery pack. It's like, we don't even carry replacements for those anymore. You know, how long have you had this? Since the beginning. Well, you know, how could this be? It's because I understood how to take care of NiCads. What I did is I made myself a dummy load, and when the battery got low, you know, I mean, obviously if it was a birthday party or something that I wanted a video, I could recharge the battery. But at least on a regular basis, I would discharge it all the way and then charge it all the way. And by the way, with nickel cadmium cells, when I say charge it all the way, that doesn't mean slap it in your quick charger. Like I've got a cordless drill at home, a Makita. I got a quick charger for it. Worst thing you could do. Mine still works. But you know how those quick chargers work? They actually have a temperature sensor in the battery pack. When the battery starts to get hot, it must be full, so it cuts the battery off. That's not a full charge. The only true method of charging a NiCad properly is a timed charge. A trickle charge where you're trickling in a known amount of current and then you bring it gradually up to that 100%. Not slam it and then the thing gets hot and then shuts off. Some of the early ones, once it would stop charging, it would cut it off, right? And then what would happen when the battery cooled down? It'd start charging again. And then it would get hot and shut down. So you ended up with this cycle in it. So these were the real cheap chargers. And those would just eat these NiCads. So if you know about NiCads weren't that bad. They really weren't. The next thing was nickel metal hydride. Nickel metal hydride. That was the next evolutionary process. Rechargeable battery, secondary cells. A lot of us had them years ago in our cell phones. Worked very, very well. Less prone to that memory condition. With all these secondary batteries, though, is it an unlimited number of charges and discharges and recharges? No. Every rechargeable battery, when it's brand new, you only get so many cycles out of it. They're not going to last forever, even if you take good care of them. And then now, lithium ion. Lithium ion. If you've got a newer cell phone, it probably came with a lithium ion. That's really the best that's out there now.
Is your Makita battery still a nickel cadmium? Do they
Yep.
still make cordless drills out of that?
I don't know. I don't know. I was thinking about that the other day because I've actually got a new battery put aside that I've never charged yet. It's still in the package. So I don't know. I've been keeping my eyes open in a store for that style pack, and I'm sure it's available on the internet. But what am I going to have to pay for it? You know. The other thing, though, too, check this out, because you know I'm not the smartest guy, but I kind of understand some of this stuff. Some of those cases, you could actually cut them open and you could replace the cells yourself, you know, and then rebond the plastic back together. And I've done that on several things myself as I've reconditioned, put in new packs. I forgot what the heck it was. It took NiCad batteries. And then what I did is I cut it open and it was just standard NiCad batteries. Usually it doesn't have the label on it, but the sizes were the same. And then what I did is I went to Harbor Freight Tools and I bought nickel metal hydride rechargeable cells, and I put the pack back together, soldered it up, good to go. Good to go. So in some cases you could do that. A lot of high performance things too, even like jet aircraft. If you're down driving past Boeing Field and you see a Learjet sitting out there, believe it or not, what they're typically going to use is not the lead acid. They're actually going to have NiCad packs. So when they start the engines on the jet, they're starting it off a NiCad, and those are very, very expensive. So it's kind of amazing. You're a multimillionaire flying around in a Learjet. A lot of times, you know what those guys will ask for? They want a starter pack to be brought over with a little tug, and there's a cart with a bunch of batteries on it, lead acid batteries, and then you plug that into the aircraft, and then what they'll do is they'll use that so they don't have to put a charge-discharge cycle in their NiCads in their precious Learjet. It's like, man, if you can afford a freaking Learjet, you can afford a new freaking NiCad, you know. But I used to work it was the funnest job I ever had. I worked part-time at an airport in Connecticut. And those guys always used to amaze me. And a lot of them would tip you. You know, you bring that pack over or whatever, and here you go buy yourself a good lunch there, son. Oh, thank you, sir. You know, I didn't mind. Some of these dudes, oh man, I'm saving you money. You're not even tossing me a bone. Come on, man. The heck. Next time I'm gonna park you out there. This is the cutaway view of a lead acid cell. Now, connecting cells and batteries. Connecting cells and batteries. We have series aiding. This chart here is erroneous. Let me draw this on the board here, what we're talking about here. Series aiding means negative, positive. I can assume that this is what voltage? 1.5 volts. So if I connect it to another cell, I can assume that this is 1.5 volts. And if I go ahead and even connect a third cell down here, I can assume that this is 1.5 volts. What am I up to right here? What's my total voltage from this point to this point? Okay, very good. 4.5 volts. Does everybody see that? Everybody see that? So what I'm doing here is by series, in series aiding, I am increasing the electrical pressure that's available to me. The amount of current that's available here is going to stay the same because this is what we call a series configuration. And current will always stay the same in a series configuration. So by connecting up batteries or cells like this, I could get a higher voltage, but current will remain the same. Does that make sense? Now down below it talks about series opposing. Series opposing would be like, okay, I got a negative and a positive here. You all agree with that? Then I'm going to connect a positive and a negative here. So I've got 1.5 volts here. And how many volts do I have here? Minus 1.5 volts. So what's my voltage across? 0. So my slide, which is politically correct, says it has little practical value. It's actually stupid. This is like, you know, you're putting a battery in backwards. Why come my flashlight no work? And you take them out and you realize you put in one of the cells backwards. Has little practical value. This one's adding 1.5 volts. This one's taking 1.5 volts away. You're putting a negative and a negative here. Current's not going to want to flow. Again, it has little practical value.
Is there any practical use for it whatsoever?
Yeah, challenging electronics students when they're going through a theory course like this. It really is. Because I could draw like 5 or 6 of these, and then you got to, let's see, plus 1.5, plus 1.5, minus 1.5, minus. So we are going to give you some problems like that have voltages. Because quite frankly, when you do get into sophisticated electronic equipment, you're going to see that there are some voltages that are being added to a circuit and some that are being taken away from a circuit. So from a math standpoint, a theory standpoint, it does have value in studying it. In parallel, and again, this is a typo here. These should not be equal signs. This should be total current is equal to I1 plus I2 plus I3. Let me show you this one. Actually, let me just go to the next slide and I'll show you on the slide. This is what we were talking about, or this is what I was talking about. I don't know if we're talking about it. That's what I'm talking about. This is 3 volts. 3 volts and 3 volts is equal to how much across this? 6 volts. Can you dig it? All right. So here we got 3 volts and 3 volts, which is equal to 6 volts, connected in parallel with 6 volts. Why come? Why come I do this? Why would I possibly, what is the advantage of this
To increase the voltage and the current?
over this? What's that?
To increase the voltage and the current?
Is the voltage increased? You said to increase the voltage and the current. Is the voltage increased? No, I still get, how much electrical pressure am I getting out of the circuit? 6 volts. What's that? Increase the capacity. Tell me more about that. I like that. Very good. Batteries are measured in amp hours. How much current over a period of time can they provide us with? So let's look at this scenario for a minute. Let's say that we all have a sailboat. Wouldn't it be nice if we all had a sailboat? We could sail off to the sunset. Let's sail up to the San Juan Islands and hang out up there. Okay? I've got a 6 volt, it's an unusual sailboat. I've got a 6 volt anchor light. So when I find a nice cove up in the San Juans and I drop my anchor, by Coast Guard regulations, I'm required at night to turn on a light that says I'm anchored. And it's a 6 volt light. The problem is this configuration here will only last for 6 hours. And then the light gets dimmer and dimmer and dimmer until it goes out. And shortly after it goes out, the fog rolls in. And here comes along a Washington State ferry. And it runs us down and it ruins all of our fun that we're having on our sailboat in San Juan Islands. So I'm a pretty smart guy. What I did is I went out and I got another battery pack and I put it in parallel with the original battery pack. The original battery pack lasted for how many hours? How many is this going to last for? For the same size load, it's going to last twice as long. How's about them apples? That's how it works. So basically, he or she who has the most batteries in parallel is going to last the longest. Plain and simple. It was actually kind of a funny story. Going to sea for extended periods of time under the water, there were very few things. I mean, even reading material, books. How many books can you bring with you? What can you do? So back in the day, the only form of media for me, basically, for music was cassette tapes. So I had my little, I didn't even have a Sony Walkman. I eventually upgraded to a Sony Walkman, but originally I had some, off-brand cassette player. And actually, that was a big advancement because prior to that, you needed the big cassette player. You put the cassette in, headphones, No 8-track. I'm talking strictly the cassettes. This was high-tech cassettes. So I bought something that looked like a Walkman, but of course, Walkman is a trademark of Sony Corporation, and this was some off-brand. So it was so funny, too, because everything that we did was super secret. You couldn't tell anybody. We couldn't even tell our spouses that we were going. So all of a sudden you see a guy in uniform, at the exchange, buying 5 tubes of toothpaste and 7 bars of soap and 100 packs of batteries, and he's in uniform with his unit, on his ball cap, and it's kind of like, you're stocking up. You guys are going to sea, So you didn't have to be like an intelligence expert to figure out who's coming and going. So anyway, we're going to go to sea, and it was going to be like a 7-month operation. That doesn't mean that we'd be totally incommunicado or away from civilized, shopping or whatever, but for at least a minimum of 90 days, we're going to be underwater. So I go out, and my cassette player took AA batteries. So I bought a bunch of these AA batteries. Well, come to find out that this thing was such a piece of crap that I could listen to 1.5 sides of a cassette tape before the batteries would die. And I'm like, I'm not a math expert, but I'm like, I'm going to run out of batteries really quick. So after I used up all my AA batteries, and I still wanted to listen to music, because again, you're living with 120 other people in a steel tube, 285 feet long, 28 foot in diameter. When you could put those headset on and you could kind of zone out, that was, a little piece of peace and tranquility you could have. So I'm like, well, I'm a smart guy. I got an electronics background. How tough can this be? So I cracked the thing up. I figured out what voltage I could wire in externally. So then what I did is every division on the submarine had different consumable products that they were responsible for stocking because you didn't have a store. So actually for my division, it was pens, pads, paper. So if you were a nuclear reactor guy, you'd come to me and say, hey, Joe, I need some pens? Be like, screw you, But no, I'd give you the pens or the paper, whatever you need. Well, ironically, the division that was responsible for providing batteries, ironically, were the electricians. So we went back and I said, I need some batteries. What do you guys got? Well, we got these sizes here. And they were the big D size, and they were military, olive drab, green, big batteries. And I'm like, yeah, give me 8 of them, So I got these 8 batteries and I wired them all up, combination series parallel. And then I got electrical tape and I this big freaking brick, And so I got this nice little portable cassette player that I paid, you know, an exorbitant amount of money for, and then I got this big brick that I'm like, so it was truly portable device, you know. So anyway, it worked, and it worked fine. And then I got so used to carrying this thing around that it was like months later, we're in port, and I'm still carrying this brick, and I even with a handle on it. And it kept working. And I'm like, why am I doing this? This thing is stupid. I actually cut it off and I threw it over the side of the boat. It's probably sitting in the bottom of the Thames River in Connecticut still. But the moral of the story is that portable cassette recorder operated off of 1.5 volt cells, did it not? What was the difference when I added the brick to it? Those are 1.5 volt cells, right? Capacity. Physically more chemical, physically more capacity, higher amp hour rating, and it kept going and going and going and going and going. So this is one of the principles for a lot of you that may pursue alternative energy, whatever that means. Basically, it's the efficiency of your cells. How many cells do you have? How much energy can you store? I actually had a student that is a project. He owns some property in central Washington. And living off the grid. Had a backup generator, also put in some photovoltaic cells. And as a project, he basically did the math and figured out, like, on the shortest day of the year, how many appliances am I going to want to run in my little cabin? And will I have enough electrical energy to make it through the night? And that's basically what his target was. And he says, I need this much storage capacity. And that's what he used as a target, and actually increased that, I think, by about 20%. And then in the summer, how many hours could he use photovoltaic to charge that? And then what's the minimum amount of time that he needs to run his generator to get those batteries up to that full capacity charge? So if you understand the math behind this, let me tell you, you're a commodity out there, because a lot of people don't have a freaking clue. They don't. They don't. When I was on a cruise a couple weeks ago on vacation, I met I'm trying to get on better terms with this guy, and actually we've been corresponding via email. He owns a 52-foot yacht in Miami and an airplane, high-performance aircraft. And he likes taking his yacht down to the Bahamas and dropping anchor. And he doesn't like running the generator. So we had a whole discussion about energy management, photovoltaic, what's the minimum amount of time that you could run your generator, can you add batteries to augment the system? And I mean, this guy, he's got a couple master's degree, highly intelligent, and he didn't have a clue of what I was talking to him about. So if you understand this, let me tell you, you got it going on when it comes to this type of stuff. Make sense? Voltage rise is the energy we put into a circuit. Voltage drop is the energy that we take out of the circuit, if you will, is given up as the electrons encounter resistance in the circuit. So voltage rise would be like your batteries. Voltage drop is what you're powering. And you know what? They should always be equal to each other. If you've got a 5-volt battery pack and you're powering a radio, that radio should be consuming 5 volts. 5-volt voltage rise, 5-volt voltage drop. Make sense? You should never end up with energy left over. If you are, that's what we call a malfunction. You've got a malfunction. You've got voltage not going from the source to the load. The voltage rise that the power company provides my house with is 240 volts AC. My voltage drop for my home is 240 volts AC. If it was 239, that means a volt is being dropped somewhere underground or in the overhead. It's not supposed to be getting dropped there. Question?
So, like, if the power company provided you with,
Voltage rise.
voltage rise.
Mm-hmm.
So, like, if you use more energy, you'd be pulling out more current, not more voltage.
Yeah, your question is more related to power. I'm talking simply voltage. I'm talking simply voltage. So that if I've got, and I'm keeping it real simplistic, and you need to understand it in a simplistic manner. If this calculator takes 3 volts DC, that 3 volts DC is going to be my voltage drop, right? If I want this thing to operate properly, I need to give it a voltage rise of 3 volts. So that's all I'm saying. Voltage rise is the voltage pressure you apply to it. The voltage drop is the pressure that gets consumed by the load. And they should always be equal. If they're not, wherever the missing voltage is, that's a problem.
So if you consume less voltage,
If you're consuming less than what the power company's providing you with, you've got a problem. Because that missing voltage has got to be somewhere. And where you find it, that's the problem. Make sense? Okay, we'll talk more about that concept, but right now I just want you to understand voltage rise equals voltage drop. Ground. Ground. This is an interesting concept. Any of you here ever driven over Snoqualmie Pass? How do you know you're going over Snoqualmie Pass? It's not a trick question. How do you know you're going over the pass? There's a sign on the side of the road that says Snoqualmie Pass. I try to keep it basic here. Now, that sign also says Snoqualmie Pass, and there's another bit of information there. Elevation. Elevation above what? North Bend? Seattle? Above where? Sea level. Oh, you guys are all smart. You guys are one of my smartest classes here in a while. High tide or low tide?
Average.
Average. And you know what we call that? MSL, mean sea level. Mean sea level. So one of the things that Al Gore is talking about, like sea level rising, that's what he's talking about. So his big concern is all the expense of changing all the signs. Elevation, no. Obviously, it's going to cause a lot of problems if mean sea level, if the polar ice caps melt and sea level rises, it's going to be a lot of flooding and devastation. Okay, especially during hurricanes and high tide events and tsunamis and everything else. So we use the height of the ocean, mean sea level, as a reference for all of our height measurements. It's actually really important. When I fly my airplane, it's one of the first instruments I calibrate when I get in, is the altimeter. And that shows me how high I am above sea level. It's kind of important. I flew my airplane Friday night. I went across the top of SeaTac Airport. I had airplanes taking off and arriving, and I'm flying through there in my small plane. You kind of think it's important that I know what altitude I'm at? Yeah. And as a matter of fact, they check back with you. When you establish radio communications, they say, you know, hold, maintain 1,500. 46 kilo, what's your current altitude? 1,500. Roger, we got you at 1,500. You're cleared through our airspace because they want to make sure you're not off. It's important to me. So that's how we calibrate if you're into hiking, driving, even boating. Mean sea level is kind of critical, isn't it? High tide, low tide. If you're at low tide and you hit a freaking rock, it's kind of important you have the right charts and you understand low tide.
Are you saying mean or mean?
Mean. Mean. No, mean. M-E-A-N, mean, which is average. So when we started playing around with electricity, we had to come up with a methodology, if you will, to what can we compare? What's a benchmark of something that's in a neutral, natural state? Earth. Why? Because this is where we be, okay? This is where we're standing. So literally what we got is a ground rod, an 8-foot ground rod, drive it into the earth and say, you know what, you connect to that, you're connected to ground. And you're connected to zero potential. It's not positive, it's not negative, it's neutral. Why? Because it's driven into the freaking ground. So what happens is, the idea kind of caught on. So the power company out at the power pole, or your transformer if you have underground, they got a rod and they drove it into the ground. They said, you know what? We're going to sell you 240 volts AC in reference to ground. At your home, at your load, you should get 240 volts in reference to ground. The electrical generating plant, where they generate the electricity, they drove a ground rod in, and they reference that voltage to ground. So we use it as a reference to all of our voltages, which are really quite critical. I'm kind of making fun of this in a goofy way, but in all honesty, it's actually really, really critical. Like right now, at my home, I've got the electrical connection coming from the power company in reference to, hopefully, ground. I get my telephone line, soon to be replaced, kicking it old school, and that needs to be referenced to ground. I've got a satellite receiver that has the antenna up on the roof. That antenna needs to be referenced to ground. The satellite receiver also plugs into the electrical outlet that should be referenced at ground, and it also needs to be plugged into the telephone connection that should be referenced at ground. Actually, when I had Comcast installed in my home, it was over the summer, I had time off, I was watching these dudes install it. And because I teach electronics, I'd always like to say, hey dude, what's going on, man? How long you been with Comcast? These people treat you okay? What's the deal? What's your educational background? What's going down? You know, how are you doing that? If I could learn something from you, somebody that does installs all day long, I'm going to pick your brain and see what I can learn. Anyway, I see this dude hooking his freaking contraption up to my faucet. I'm like, what are you doing? He said, I'm connecting this to ground. We got to reference it to ground. I'm like, hold on, cease and desist. What are you doing? Well, I got to connect this to ground. I said, that's my freaking water connection. Well, yeah, but this is, water pipe is a good ground. No. You see that right there, driven into the ground? That's a ground rod, okay? That's the same ground rod that the power company's providing me with ground. It's the same ground that everything else in the house is connected to. So why are you going to connect it to this faucet coming out all? You don't know if it's PVC inside. He really got an attitude, and I'm like, no, boom, cease and desist. I got a supervisor out there, and I had to sign paperwork, modified install. Modified install? Customer request, I want ground, and I wrote that right in there. Me want ground to be connected to ground rod. So they all really got an attitude and stuff, but it's kind of like, no, I mean, it really needs to happen, because especially, too, this is back in the day when you had a computer modem. You could have that modem, you could have your computer power supply, you could have all these things, and if they're not all connected to ground, they could develop a difference in potential. And if they develop a difference in potential, you know how that's going to manifest itself with highly sophisticated electronic systems?
Sparks and fire.
Not necessarily sparks of fire, it could be gremlins. It could just be real wacky behavior. All of a sudden, your satellite receiver starts rebooting itself. All of a sudden, your computer reboots itself. All of a sudden, your modem kicks you out. So when they started doing all of this inter-building networking and everything, it became a real big issue to make sure that ground was really ground. Years ago, when they built this building, well, actually, they renovated this building. Behind here, they pulled up the concrete, and they drilled down into the earth. And they put in this huge ground for the school to make sure it wasn't just a standard ground rod. This was like drilled way down into the earth. You can see like the core and stuff. No, I'm just kidding. But it was pretty far down in. This is actually one of the problems that they have like in Arizona because of the sand and the desert. And we have good ground here because it's like all wet. But in Arizona, they have some problems. So I think there's some code variants down there where they're like actually connecting it like rebar in the concrete foundation and such, and they do some different stuff down there. I'm not totally familiar with it, but some of those dry climates, they have to do it. John?
How big was that? Was it a pipe or a...
It was, and they were actually adding chemicals to almost create like a P and an N type material there, so current would only have one way to travel through that, like a giant diode buried in the ground behind here. So I wish I had taken pictures. So I know you're not believing me, but it was like a drilling rig out there. It's like black gold, Texas tea. We're going to Hollywood, Anyway, the other type of electrical ground is electrical ground, and this provides a common reference point. We use this electrical ground because the 747 taking off would look stupid with a big reel, spool of wire trailing behind it. Okay? It just wouldn't look right. So for pure aesthetic purposes, We can't do this. So we use what's called electrical ground. Your car uses electrical ground. Airplanes use electrical ground. Ships use electrical ground. And what that in essence means is a chassis ground. Now most of our home appliances use both. We ground the chassis, the electrical ground, to earth ground. So that if you have a 3-prong plug, one of those plugs, that round plug, is ground. And that's connected to the chassis. So be aware of this. In the lab, you're going to have some problems with ground because you don't understand what I'm talking about. Some of the equipment that we have in the lab is isolated from ground. So when you connect the negative lead, like on a power supply, you think you're connecting ground as a chat. You're not. That negative, if you have a DC power supply in the lab, you have a positive, you have a negative, they're isolated from ground. They have nothing to do with earth ground. So in some cases, you could create a ground loop in there and they get wacky results with your equipment. Most commercial, consumer, industrial products are for the purposes of electrical safety. That chassis will be a ground, and that's connected also to earth ground. Question?
Oh, so electrical ground can vary from whatever you want it to be. Electrical ground.
Absolutely. Absolutely, and that's one of the things that can be a real problem, is you might think you get into a piece of equipment and say, oh wow, look at this big metal, look at this big, if this was inside, this is actually a DC power supply like we use in the lab, okay? This in the back here is a heat sink. If this was installed inside some big piece of equipment like a radar system, you see this metal, you assume that, oh, this metal here, that's ground. That must be ground because it's metal, right? And all of a sudden, you know, you put your hand on there, or you lean into it, and you get electrocuted. This, in some cases, could be electrically isolated from ground. This could be connected to some big high-power transmitter tube for the purpose of dissipating energy, and it could actually have, like that mica that I passed around earlier, it could have a big sheet of that mica there electrically insulating it from the rest of the chassis or frame of the piece of equipment. And that's taken out many a good technician. So never assume. Never assume. Generally, yes. Some of the worst shocking experiences I've ever had were working on a lot of tube circuits, because sometimes those tube circuits were notorious for 2-prong, old school tube amplifier. You plug it in 2-prong, and you didn't have that electrical ground in there. All of a sudden, you go up against the chassis, and you're getting zapped by 300 volts. Make sense? All right. We talked about current. Flow of electrons in a specified direction happens at the speed of light. Voltage. And there's only 6 different methods of producing voltage: friction, magnetism, chemicals, light, heat, and pressure. We talked about voltage rise. That's the energy that we put into a circuit. Voltage drop is the voltage we get out of the circuit. Voltage rise and voltage drop should equal each other. If they don't, you got a problem. Am I being silly? Am I keeping it basic? Yeah. But you know what? I have fixed in my career dozens of problems that was the symptom. And the symptom is the equipment doesn't work right. What's the first thing that I do? Check the voltage coming in. If the voltage coming in isn't good, it's not going to work right. Then you got to find out where the missing voltage is. Maybe it's a brownout. Maybe it's a brownout. Maybe the power company, they're having a problem with generating power and giving, you know, the feed. But those two always need to equal each other. We also talked about ground. Earth ground is a freaking rod driven into the earth. Why the earth? Well, it's where we stand. It's where we live. It is what it is, neutral natural state. And we talked about electrical ground, which is typically the chassis. Could be the airframe of an airplane, which is actually kind of odd. It's kind of odd when I talk about an airplane, because what's Boeing building now? 787. What's that thing made out of? Aluminum? Composite. Think about this one. By using the chassis of your automobile as ground, you know how much wiring it saves on your car? Go ahead, make a stab at it. You know how much wiring it saves on your car? It saves half the wiring. If your car was made out of composites and it was not a conductive material, you would have double the amount of wires on your car, because we use the chassis as an electrical connection. Make sense? Okay, I've got a question for you, and I'm going to ask you about this in our next lecture. And I want you to discuss this in teams and as a class. Since there are 6 different methods of producing voltage, I am going to design a deep space probe to boldly go where no man has gone before. So this deep space probe is going to probe deep space. That's why it's called deep space probe. What method should I use to power this thing in outer space so that it keeps going and going and going and sending data back to Earth through a high-powered transmitter so we could monitor its journey from afar? I want you to think about this. I want you to discuss it as teams. And next week when we lecture on ELEC 110, I'm going to expect an answer from you, and it better be the right answer, or all hell's going to break loose. Any questions? Question?
Kind of in reference to the question, I always wondered why radioactive materials are radiating something, right?
Yep.
I'm assuming it's radiating electrons.
It's radiating something, absolutely.
I always found it strange, like, that we were never able to figure out a way to generate electricity out of the radiation itself instead of...
Sounds like you got some good ideas that are worth pursuing. Enough said.
Okay.
We got somebody in here that's thinking. That's cool. Question?
How do you measure ground?
How do you measure ground? It is measured in ohms. What you do is you have to, it's a comparative process of what you assume is a good ground. And you're basically comparing your ground, unknown ground, to that good ground. But there's an assumption made that by getting an 8-foot long rod in driving it in, that is providing you with an adequate ground. You need something else to compare it to in order for your assessment to be accurate.
So when you take a multimeter to test ground and it measures the material, does that multimeter have a
What are you measuring it in reference to?
I don't know, an electrical outlet, let's say.
Okay. What you're doing from like an electrical outlet, if I wanted to verify that this is a good ground, in actuality, what I need to do here is I could measure ground against my neutral. Those two should be connected back at that box. Okay? So between the hot lead and ground, and between the hot lead and neutral, I should end up with the same difference in potential. Then going with a multimeter to that box, I should get that same difference in potential across the two. And that basically is letting me know that the ground and the neutral for that particular circuit are valid. But for you to compare a good earth ground to a not so good earth ground, I don't know how you'd go about that, other than you've got to basically know that one of them is good. And that's actually one of the things about ground too, that I don't know if any of you are aware, a lot of AM radio stations are located in swamplands. It's the best place that you could put an AM radio station, because in a swampy area you get a really good ground. So you get a really good ground plane. And because of the frequencies that you radiate at, it's going to ensure much better transmission of that RF signal. A second choice is also a field, a pasture where cows graze and urinate and keep everything nice and moist, okay, and healthy. That's why even in New York City, growing up in Connecticut, all the New York City radio stations, WABC, WNBC, WCBS, all of their transmitters were located in New Jersey, the Meadowlands. Okay, if there's any Giants fans here, it's where all their transmitters were located. Why? Because it was a marshy location. FM transmitters, different. If you're in New York City, where do you want to put an FM transmitter? top of the Empire State Building. Why? Because it's the highest. It doesn't have as much to do. You still need a good ground, but it's not as essential as that low frequency transmitters. So ground is important, folks. We're going to talk more about it. We could have a course in ground. We honestly could. 5-credit class and just talk about ground. Testing processes, you know, some of the different things that we've encountered with ground. 50 years ago, 30 years ago, 20 years ago, ground wasn't that big of a deal. Ground right now is very, very big because a difference equates to a difference in potential, and even a small difference in voltage could create a circuit and cause that circuit to go, here's your final technical term for the night, cattywampus. All right? All right, that's all I got, folks. Have a good